Hey everyone, and welcome to This Explainer. Today, we're jumping right into a really fascinating topic, the hero's journey of databases. For decades now, database architectures have been constantly evolving, kind of mutating and upgrading to conquer entirely new monsters of data. We're talking about a journey from the early days of simple digital filing cabinets all the way to the mind-bending realms of artificial intelligence. The way we store and retrieve human knowledge has just completely transformed over the years, and it's a transformation that literally affects every single app you open on your phone today.
So, here's our roadmap for today. We're going to cover the database scaling problem, how we control transactions, the NoSQL revolution, the rise of NewSQL, and finally, the AI database frontier. Let's see how these architectures evolved through escalating eras of technology.
All right, let's kick things off with Section 1, the database scaling problem, escaping the single server. Traditional relational databases were absolute workhorses. They were perfectly designed to scale up. You just had to build a bigger, more powerful single server. But then big data arrived. The extreme volume, variety, and velocity of information basically forced engineers to completely abandon that single server model. The solution? Distributed databases. Instead of one giant machine, workloads are spread out across multiple interconnected nodes. But while this brilliantly solved the storage and processing limits, it introduced a massive new headache. Think about it. How do you keep data perfectly synchronized when it's being read and written across dozens of different servers at the exact same time?
Well, that brings us right to Section 2, controlling transactions, managing the traffic jam of data.
To stop simultaneous transactions from just completely crashing into each other across those different nodes, systems desperately needed strict rules. Concurrency control acts as the ultimate traffic cop for distributed data. Without it, you get lost updates, you get read inconsistencies. Imagine two people trying to buy the exact same last airline ticket at the exact same millisecond, just on different servers. Concurrency control is the mechanism ensuring only one person gets that ticket, keeping the whole system accurate without slowing everyone else down. To manage this crazy traffic, engineers essentially split into two camps. On the left side of the family tree, we have pessimistic approaches. Think of these like strict stoplights at a busy intersection. They lock down data using methods like two-phase locking because they assume conflicts are absolutely going to happen. So they freeze traffic to ensure accuracy. But on the right, we have optimistic approaches. These act way more like high-speed traffic circles. They assume conflicts are actually pretty rare, letting transactions flow concurrently, and only checking for rule violations at the very end. And wow, did the optimistic approach show massive promise. For example, an algorithm known as ACOC, that's Adaptive and Speculative Optimistic Concurrency Control, yielded a staggering 35% throughput increase. Just by prioritizing validation at the end of a transaction rather than applying those restrictive locks right at the beginning, systems could process significantly more data in way less time. But hold on, it actually gets even better. By pushing the boundaries of this optimistic methodology, researchers developed TikTok. And I just love this name. It stands for Time-Traveling Optimistic Concurrency Control. The results were absolutely incredible. TikTok achieved a 92% throughput enhancement along with a massive 3.3 times reduction in transaction abortion rates. This basically proved that smart validation was often vastly superior to rigid locking. Let's move on to Section 3, the NoSQL revolution, embracing the chaos for infinite scale. So even with that amazing concurrency control, the rigid rules of traditional SQL databases were still holding back infinite web-level scale. This led to a really radical paradigm shift in database architecture. NoSQL entirely abandoned the strict ACID reliability, atomicity, consistency, isolation, and durability that traditional databases relied heavily on. Instead, they embraced the wild, horizontally scalable frontier of base principles, basically available, soft state, and eventually consistent. They literally stopped worrying about perfect, immediate accuracy just so they could achieve unprecedented speed and scale. This rebellion was largely driven by the CAP theorem. This theorem famously proves that in a distributed data store, you can only simultaneously guarantee 2 out of 3 elements: consistency, availability, and partition tolerance. Big data systems, like massive social networks or huge e-commerce sites, demanded partition tolerance and availability above all else. Because of the CAP theorem, NoSQL systems were forced to compromise on strict consistency just to keep their websites online and lightning fast during those massive traffic spikes. Which leads us to Section 4, enter NewSQL, getting the best of both worlds. Now, the NoSQL compromise of eventual consistency is totally fine for a social media feed, right? But it wasn't nearly enough for critical financial networks or business systems that absolutely required strict, unshakable data integrity. I mean, you definitely can't have your bank account balance be eventually consistent. So to solve this, new SQL engineers created a hybrid. As you can see, NewSQL finally achieved NoSQL's horizontal distributed scale, but perfectly maintained traditional SQL support and strict ACID guarantees. Systems like VoltDB and NuoDB completely broke through legacy limits by utilizing in-memory processing and advanced shared nothing architectures. All right, our final stop, Section 5, the AI database frontier, the next mutation. Just when we thought we had mastered big data with NewSQL, an entirely new species of technology broke all the rules yet again. We entered the era of large language models. These AI systems do not think in neat rows and columns. They process concepts as massive, multidimensional mathematical vectors. And this threw a massive wrench into our beautifully engineered relational architectures. When you try to force large language models to rely solely on their internal training or on traditional databases, they stumble over these exact critical issues. They suffer from AI hallucinations, which, by the way, is exactly why your chatbot might confidently invent a totally fake legal precedent or historical event. They also possess outdated knowledge because their training data has a hard cutoff date, they incur wildly high commercial application costs, and they struggle with complex memory retention. Without specialized data storage, LLMs are just unreliable and far too expensive to scale effectively. Enter the ultimate cure, vector databases, or VecDBs. The explosive rise of vector databases offers an efficient, high-dimensional storage solution to cure these LLM bottlenecks once and for all. Because instead of just storing a word or a number, a vector database stores the actual meaning and context of a data point across hundreds or thousands of dimensions. This allows the AI to instantly retrieve relevant concepts through mathematical proximity. It's a real game changer. By fundamentally transforming how we store, retrieve, and manage knowledge itself, vector databases are effectively giving large language models a reliable, infinitely updatable, long-term memory. We are literally witnessing the bleeding edge of the next database revolution here, directly addressing the limitations of the AI models that are actively reshaping our world today.
So we've gone from single servers to distributed systems, from NoSQL compromises to NewSQL hybrids, and now into the mind-bending, high-dimensional space of vector databases. Our data architectures have constantly adapted to survive. But as AI evolves from simply processing text to generating entire worlds and simulating complex realities, what impossible architecture will databases need to invent next? I'll leave you with that provocative thought. Thanks so much for joining this explainer, and keep questioning the limits of our digital world.